last session, we defined what an acid and a base was. We looked at them as they're a paired reaction. Just like oxidation reduction, we've got acid and a base in these here that we're going to be looking at. And in essence, we said that the acid base gives a conjugate acid, conjugate base. And we did a few of those. We looked at how a mono, a di, or a triprotic acid ionizes when it hits water. And we're now going to look at, let's have a look, we're going to look at strong and weak acids. Strong and weak acids. Okay. How do we define it? If you remember, how do we define it? We do it through Ka, which is the constant for water. For the acid. Ka is the equilibrium constant for an acid. While we're about it, Kb is the equilibrium constant for a base. Okay? What it means at that point that the ionization process as such has reached equilibrium. The other part is to say, oh, all right, that's fair enough. Now, let us look at an acid, HNO3. Okay, let me put the phases in now. I've been a bit lax. Aqueous plus H2O, liquid. Equilibrium reaction, we say this is going to H3O plus, aqueous, plus NO3 minus aqueous. That is an equilibrium reaction. Therefore, and it's an acid, so it gets a Ka, is going to be the concentration of the H3O plus. We did a lot of these in the previous section on NO3 minus over the concentration of HNO3, aqueous. These are all aqueous. And I've left water out because it is a 1. We use a 1 for the water there. All right? Now, on top, therefore, we have product. On the bottom, we have reactant. Shall I put that in capitals? Probably. Okay, reactant. Well, it's quite straightforward. We've done it, we've seen it before. If Ka is large, then lots of product, because the top is bigger than the bottom. 4 over 2 is 2. 6 over 2 is 3. Therefore, what we're saying is that the top is bigger. We're getting lots of product. Similarly, if Ka is a small number, okay, you have lots of reactant and little product. Correct? What it means is that therefore ionization very little. Okay? Not much H3O plus. Here we've got lots of H3O plus. Correct? Because it's a product. Therefore, the higher it is, the more it's ionized, the less the reactant. It's all split up into the H3O and the conjugate base portion. This is quite straightforward. Okay. The next is, remember, just so that in passing over here, little, we've got that, and yes. Now we make our definition. Just put those two back. And we call this one strong a strong acid. All right, and the one underneath, let's change it to green. This is going to be a weak acid. It will be a weak acid. Lots of H3O, strong acid. Little H3O, weak acid. It's meaning that it has not ionized very much, and we still have a lot of reactant left if it's weak. What if we look at a base? Let us look at a base as an example, and I'm taking NaOH over here. I'm omitting the water because it's not really relevant. I'm just doing it ionically because it's easier to grasp. Therefore, K, in this case B, is equal to Na plus aqueous over OH minus divided by NaOH, aqueous, like that. And once again, the water gets left out, so I didn't bother with it. That is Kb. The same things apply. If Kb is high, therefore, lots of product, same thing, product over reactant. Can you see it's exactly the same? Lots of product. In this case, lots of OH minus. And this is our base measurement, isn't it? The H3O is the acid measurement. The OH minus is the base measurement. And if Kb is very small, therefore, little product. Okay? Therefore, not much OH minus. Not much base. That is pretty self-explanatory. It's the same as the acid. The concept is what we're after here. We're after getting the concept going of what is happening. So we can go back up and I can say that same story. Let's go back to the red. This is a strong base. Because there's lots of it. The bottom one is a weak base because I get little of it. We can do it with ammonia as well. Let's look at this one. Because these are the ones that come up often in the examples. NH3 plus H2O in equilibrium going to NH4. Write the expression of mass action for this, for example. We would say what happened here? The NH3, right? The NH3 is going to be accepting. There's my acid. Therefore, I say, right, the Kb is going to be the concentration of the NH4 plus times the concentration of the OH minus. This is my base divided by the concentration of the NH3. This is an equilibrium reaction. If Kb is low, it's a weak base. If Kb is high, it's a strong base. Same applies to that. I left the water out because it's a liquid, and liquids and solids are one in the equilibrium constant reaction. Lastly, before we move forward, we need to look at Kw, which is ionization of water itself. Remember we said that H2O plus another H2O can go to H3O plus an OH minus. One of them, this is the acid, plus the base, goes to the conjugate acid, plus the conjugate base, like so. And we remember, we said, right, we're now going to put down the dissociation, or rather the equilibrium constant. It's Kw, which is for water, is equal to the concentration of H3O plus times the concentration of OH minus. is 1 times 10 to the minus 14 at 25 degrees Celsius, and in this case delta H is greater than 0. We have done this in the previous section, therefore we're just recapping it currently. We thus have now dissociation constants Ka, Kb, and Kw. Please note over here, I'm going to put it in, that 2 moles goes to 1 and 1. This and this are the same. This and this are the same. Therefore, in any situation, you can work out x squared must be equal to that. Therefore, the concentration of the H3O must be equal to the concentration of the OH minus, 1-to-1 ratios, which is going to then be equal to the square root of 1 times 10 to the minus 14, which is going to be 1 times 10 to the minus 7 moles per cubic decimeter. That's what we've got. Now, we will be getting back to those a lot because they're going to become our standard formula when we start looking at how do we measure this. The word pH is going to come up very soon. Let's just look at what happens when we add an acid and a base to pure water. Okay? Let's just look here. Okay? This is pure water, so we've got H plus and OH minuses in here. Now we're going to add an acid. Let's make it red. We're going to add an acid. Let us say that is, for argument's sake, HCl. Essentially, we're going to add that, so we're going to increase. We're going to increase the H plus, aren't we? I'm going to just change that H plus to an H3O because that's the way we need to look at it, all right, technically. So we've got H3Os over here and an OH minus over there, and then we are adding in more H3O from the acid. So therefore, concentration of H3O ion is increased, goes up. We've added more. The equilibrium reaction says Kw is equal to concentration of H3O, concentration of OH minus. Must be always 1 times 10 to the minus 14. Which means what? That as the H3O goes up, therefore the OH minus must drop to keep the concentration of H3O times OH minus equal to 1 times 10 to the minus 14. Okay. OH must decrease. If I add H3O, OH goes down. Right, yes, you've guessed it. The next one is going to be if we add a base to water. I'm going to put the water here. There's our water. Here's our H3O plus and our OH minus. And now I'm going to add a base. Add a base, which means I'm adding OH minus. So therefore, there's more OH minus. What does that mean? More OH minus. More OH minus. Therefore, the concentration of the H3O ion must drop. Because this one goes up, this one must go down in order to retain the situation. So we're ending up, if I add a base, in a base added, okay, I will end up with more OH minus ions in the water, and with an acid added, we get more H3O plus ions in the water. Absolutely straightforward logic. Okay. The last part, well, not the last part, but now the point is we say, all right, how do we tell? How do we do measurement of this? The measurement of this situation. Measuring acids, acidic or basic. Here we go. We define, okay, we define pH equal to the negative log of the concentration of the hydronium ion. We define the pH as being that. End of story. That's what we're going to do for the moment. That's what it's going to be. Now, we have got a pH scale. And the pH scale is going to go along here, and we're just going to talk it through. Right in the middle is 7, 0, and 14. Okay? This is theory in the textbook. I'm not going to spend a lot of time on it. Down this end, I'm going to use red. This is acidic, and I'll use green on the other side. This is basic. 7 is thus, let's use blue. The last one, 7 is neutral. It's in the middle. It's neither acidic nor basic. And what we've got there is that's our pH scale. Now, when we put litmus paper or universal indicators or phenolphthalein, methyl orange, bromothiamyl blue, and a whole pile of others, including a pH meter, we are going to see a number on a scale. We've now defined that number. It's the negative log of the concentration of the hydronium ion. So, here we go. How do we approach these problems? Right? Well, first of all, you use a balanced approach, balanced equation. For everything in chemistry, right? You use a balanced equation. Let's just pick one. I've got here an example. I just go back to black as I always do. Calculate the pH. Here they say, calculate the pH of 0.5 grams of H2SO4 in 500 milliliters of H2O of water. Step 1 is a balanced reaction. Therefore, we say H2SO4, right, aqueous, plus H2O is going to go to 2 H3O plus SO4 minus 2. My reaction thus, I put my recipe is 1 plus 1 goes to 2 plus 1. Like so. Sorry, there's 2 waters there. My bad, I thought so. Right, there's 2 because I need, that must balance out I hadn't balanced my equation. So what do I say? I say, all right, I start with given. What am I given here? I am given, they have said, 0.5 grams. Okay, and they've also given me a volume of 500 milliliters. The first thing we do when we're given that, decimeters cubed, we change it, that is half a liter, is half a decimeter cubed. Why? Just to recap, I'll do it in red. 1 decimeter cubed is 1 liter. 1,000 milliliters, okay? So where we're going now is we're going to calculate the pH. Right, pH means means the concentration of hydronium ions is what we're after. So I have to get to moles as always. Given, now I need molecular mass because I need to get to number of moles. So molecular mass of this is 98. It's 2 plus 32 plus, just to recap, 16 for the oxygen times 4, which is going to be 98 grams per mole. 98 G mole minus 1, same thing as my little stripe. Therefore, N is going to be equal to mass over molar mass, which is 0.5 over 98, which is 5.102 times 10 to the minus 3. I always say to students, use 4 places. Use the 4. Now I can go through the mole hole, correct? We can go through here because 1 mole, the recipe is 1 goes to 2. I'm after this H3O. So therefore, I've got how many moles? 2 times that. 2 times 5.102 times 10 to the minus 3 is equal to 0.0102 moles of H3O plus ions. That's in my water, 0.0102. My next one is to say, okay, I understand, but I am looking for concentrations. Always we're going to the concentration. Therefore is 0.0102 divided by 0.5, which gives me 0.02041. That is moles per cubic decimeter of H3O. Therefore, that number is the concentration of H3O plus, is it not? We have found the concentration of H3O plus. Now the pH is straightforward. The pH says, right, what do? The pH is equal to negative log of the concentration of the H3O plus. Therefore, it must be minus the log of 0.02, 0.02041. And you just use your calculator, and that gives you 1.69 is my pH. And you immediately say, it's right, it's an acid. So it sounds about right. Okie dokie. Where am I going next? The next one, let's do another way around. I said, here we go. Let's say the mass, okay, calculate, question 2. Calculate the mass of H3PO4 needed to ensure a pH of 2.0 in a flask, in a 250 milliliter flask. All right? Okay. Now in this case, we know that acid there, but we want to know how much of that must we put into the flask. That's what we're after here. So what I'm saying is, what are we given? We're given a pH. So we say, right, pH equals negative log of the concentration of the H3O plus. But they've told me the pH is 2. Therefore, 2.0 is the negative log of concentration of H3O. I'm given a pH. When I'm given a pH, start with the pH. Hello, where do we start these things? Where we've got the most information. And that's right there, isn't it? So how do I do this? This is minus 2.0 is equal to the log of the H3O plus ion. Now, for those of you who are not sure at this point, do you remember, if you look at your calculators, you will see sine, cos, and tan. Above it, you will see sine to the minus 1, cos to the minus 1, and tan to the minus 1 on most of them. This is kind of like the opposite, isn't it? Now you will see a button called log, and at the top you will see 10 to the, and I think it's actually got a block over there. like so. This is, here I want that. So essentially I'm going to press Shift log, and you will see it will then be 10 to the minus 2 is the concentration of the H3O plus. My final answer is thus, it's going to be, where are we, 0.01. And it's a concentration, so it's moles per decimeter cubed is the concentration of the H3O ion. That's it. The next is we said we need a balanced reaction. So we go to H3PO4, H3PO4 aqueous plus 3 H2Os are going to go to 3H3O plus PO4 minus 3. And I now go and I say, right, my mole ratio is 1 to 3. Here's my thing, 3 to 1. So now let's look, what are we given? All right. We are given a concentration of this. Concentration C, in fact, let's do it how we used to with the others. Instead of the brackets, concentration of 0.01 moles per cubic decimeter. That's what we're given. There it is. That's what we have to have in there, is that amount. So what do I do now? Well, where am I headed? I'm headed for the mole hole, N. I need this mole hole. Without it, I can't do anything. So I need N. In order to get N, what have I got? Volume was 250 milliliters, which is 0.25 liters, which is 0.25 decimeters cubed. Therefore, number of moles is going to be equal to, and in this case, you're just going to multiply it out, and I have concentration, 0.01 times 0.25, which is 2.5 times 10 to the minus 3. That's the number of moles. Now I go to my mole hole and I say, okay, cool, now I can go through. Now, this reacts in the ratio 3:1. Therefore, how many moles of H3PO4 did I need? I needed number of moles of acid is going to be 2.5 times 10 to the minus 3 divided by 3, which turns out to be 8.33 times 10 to the minus 4 moles. That's how many moles of acid I needed. Then they say, okay, what mass? I go back and I say, all right, they are asking me for the mass. I've got N, therefore I need the molar mass. The molar mass of H3PO4 is 3 times 1 plus 31 plus 4 times 16, which is 98 grams per mole, I think. All right. H3PO4, 331, 4 times 98 grams per mole. Therefore, what the next thing is I say, right, therefore, the mass is going to be equal to 98 times 8.33 times 10 to the minus 4. Okay, which gives me 0.082 grams. I'll just check the molar mass is going to be 4 times 16 is equal to that, plus 31 is equal to that, plus 3, it's 98 grams per mole. And my SO4, yeah, all right, 98 is 2, 32, 16, 32, all right, 2, 1, yeah, cool, 98 grams per mole, and therefore the mass is molar mass times number of moles. How do I work that out? Number of moles is equal to mass over molar mass. We have done that one a million times. We are going to go through and we're going to work out further examples of these using pHs, but I've got to stop it at that point because, as I say, we're trying to do everything in 30 minutes. We're going to carry on in the next one, the third one, where we're going to look more at these examples. I'll see you later. Cheers. Have a great one. Bye.